to pitch this presentation because as you heard from the introduction, I come from an engineering school, so most of my presentation will probably be designed for engineers. So I'll try and just go fast towards some of the technical bits. So my presentation is about recycling of composite materials. So in the UK, we're looking at an increasing use of composites, mainly in the aerospace sector. And because of the increasing use of composites in the aerospace sector, we're thinking what will happen 20 years or 30 years down the line when we have to recycle the composites or when products are retired. So we set up a group looking at how do you bring these composites back to life, what are the appropriate recycling processes. My main interest was looking at how can we do that in an environmentally sustainable way. So the last question, I think, to our first speaker was about life cycle assessment. My main interest is how do we develop the data sets to support life cycle assessment. So if you have a recycling process, we need to assess it in terms of the environment. How do we know how much energy it uses? So that is where we're coming from. And to support that, we looked at the value of composite waste that's available in the UK, and the main driver here is that a number of European directives that are going to limit the disposal of composite waste to landfill. And we're trying to find out how can we generate this as a business for a number of companies. So before I start, we're looking at composite materials, and there are mainly two classes, thermoplastics and thermosets. And thermosets are difficult to recycle, so my presentation will be mainly focused on thermosets. And these thermosets are also widely used in high critical applications. So your aerospace applications mostly use thermoset composites. So what is the challenge? So we have two classes of materials, one based on glass and one based on carbon. So we have a lot of glass reinforced composite material, so significant volume, but we have a small quantity of carbon fiber reinforced composites, but high value. So there's high quantity and high value, so there are two drivers here. So if we can recycle as much glass as possible, it will be good for the environment. If we can recycle as much composite as possible, then we can make money because of the cost associated with composite fibers. So a number of directives here that are driving the recycling of composite materials. So what we started doing is to try to understand how much scrap or composite waste do we have within the UK supply chain? Because if you want to recycle something, you need to know what's the quantity that's available. So we looked at this approach, which are called Sankey diagrams, a very useful way of modeling resources within a supply chain. So on a Sankey diagram, the thickness of the arrow here represents the quantity. In this case, this will be the tonnage of GFRP within the UK supply chain. And you can see, as I said before, we have more glass than we have carbon, so the thinner line here. And what's coming out here are the scrap material which we're trying to recycle. And this scrap here originates from manufacturing processes, so production processes that generate scrap, and also from retired products. So we're looking at how do we reclaim this and bring it back to life. So why are we doing this? The primary reason is to recover the high-value fibers, but we are also interested in this fact here that composite materials are very energy-intensive to make. So if we can recycle them, then we are cascading the value that we have already invested in primary production of the composite materials. We are also looking here at the high value in terms of the contribution to the UK economy, and I have some values here. So carbon fibers, quite expensive, glass, quite cheap. So companies are interested in if we can reclaim the fibers, can they sell them? But I'm more interested, can we do it in an environmentally friendly way? And how can we decide which is the best process to do it in terms of the environment? So to set up this study, we have a consortium. So a number of universities in the UK indicated here, mainly according to the cities where we are, Birmingham, here Manchester, and our colleagues at Cranfield and Exeter. So what we're trying to find out is how do we minimize the environmental burden associated with using materials and reusing materials. And we also make an observation here that most of the processes that we use to reclaim materials or to make products are actually energy intensive. And how can we decide which is the best process in terms of energy efficiency? And we also look at some of the challenges here which hinder the use of recycling broadly. And the last observation we make is that while we want to recycle composites, it's very difficult to find enough composites sorted already. Everything is mixed up with something else. So we're not good at sorting our waste in terms of as a world community. So ideally what we would like to do is to assess the life cycle impact. I think that's the question we had before. So the life cycle impact of using a product. And what I'm saying here is in terms of composites, most of the impact is associated with production of virgin materials. And when we shape this into useful products, use them and recycle them, there's less energy here than the energy that is at the first process. So if we can reuse materials, then we can cascade that value that's captured in the first process. The second point and observation is based from work done by other researchers, which says that if you look at the way we shape materials, you can rate the methods by the energy intensity, so how energy hungry they are. Some processes are very good in terms of the energy they use. Other processes are very much energy intensive. Unfortunately, it tends to be the new processes that are more energy intensive. So we're trying to understand this so that we do not end up developing processes we describe as innovative but not good for the environment. So that's one factor, that some processes are more energy intensive than others. The second factor that affects recycling is captured by this diagram here, which were called the recycling boundaries. So the initial concept was developed by a chap called Sheld, who looked at the concentration of ore and postulated that it's more economical to mine something if it's of high concentration. So in the same way, if you have a product like that with composites, it will be more economical to reclaim the composites if the product was predominantly composite. So what this diagram says is that we can derive a complexity measure which looks at the ratio of materials within a product, and we look at the value, and we can almost draw a line where some products are more economical to recycle and other products are too complex to recover materials. So they are also, beyond the technologies, there are limitations to recycling which are imposed by the nature of products. So in a circular economy, we should look at how you redesign products to make it easier to recycle them. So within that context, we are looking at composite recycling processes and how do you typically do that. So you find a big block of composites, so it could be as big as this lantern here, and we need to dismantle, so we need to break this into pieces or disassemble it, and then we need to downsize it, and then we need to recover the fibers or the resin here, and then we need to do some post-curing process. So this is the full process, but I'm just going to focus on this particular circle here, though the other processes are also important. So how do we do that? We can use heat, so thermal processes. We heat the composite, and therefore we decompose the matrix. We can use microwave radiation, which is good because we can do that through volumetric processing. We can also use chemical processes, or we can do it mechanically, or we can use high voltage fragmentation. So there are different ways of separating materials. So through this consortium, we are addressing the range of processes that I have described. That's just an example of the simplest process, which is the mechanical process, which I will show here. Just a quick view of how this works. So I've got my granulator here, and I'm feeding my composites here. Hopefully this goes as fast as it should. So basically what it is, it's a big milling machine. I've got my composite panels that I want to process, and these panels, I'll put them through the chute in the hopper, and through some downsizing process, which is happening here. Unfortunately, it's not updating as fast as it should. And then I'll end up with a range of reduced size in terms of materials. And this is the original one, the final product. And I can have different sizes here. So you can already see that there's a limitation if I use the mechanical process in terms of how clean I can get the fibers. So alternatively, I can use microwave radiation. Therefore, I just heat the matrix, and I'm able to recover the fibers in a better form. Or I can use high voltage fragmentation. So imagine here, I've got my composite material, and immersed in a bath of water, I generate a high voltage here, and then I'm able to generate a shock wave. And this is the equipment inside, and that's the result. So I started with my composite fiber. Through the shock wave, I'm able to fragment the composite, and then I wash out the resin, and that is the remaining material. So the other process I could use is chemical processing. So in this case, I start with these composite panels here. Through some acetone-based solution, I'm able to recover the clean fibers here. And so that is done by our partner in Birmingham. So if we look at all these processes, how do they compare in terms of the quality of the fibers recovered? So you see here, if we take the original material as 100%, and you see what tends to happen is that these processes generate a wide range of fiber qualities, and this is the research challenge to reduce this gap here and try and aim for the top band. And we're also looking at products made from the recovered fibers. Again, you can, for some processes here, like chemical, you can get close to 100%, which means you're retaining the value of the fibers. But how do we know how energy intensive they are? So my research is looking at what I call bottom-up inspired modeling. So if we understand the process that we use to recycle, then we should model all the resources that we are going to the process and use that as an input to life cycle assessment. Because we understand how much materials, how much energy goes in, we should be able to objectively or scientifically evaluate how much the resource is intensive in terms of energy. And with most production machines, if you're using a machine to recycle, what tends to happen is about 80 or 90% of your energy goes into the machine, whether you're recycling or not. So if you've got a chemical plant and you just switch it on, or you've got the granulator I was showing before, most of the energy goes into the equipment. It doesn't actually go into the recycling process. So the economics or the environmental footprint of recycling is really favored by how much volume we can put into the equipment so that we can extract more from the energy-intensive process. So we model that mathematically using equations, so I'll spare you the details. And that's my machine. And what we're doing is we're trying to say, according to a certain volume of composites processed, how much energy is used. So we model that and we validate it by actually doing some recycling, and we come up with some equations. So what is really interesting here is that in terms of the life cycle impact or the energy intensity of your process, the faster your recycling process is, the more energy efficient it becomes. So if you've got an industrial process, it will probably running here, but if you've got a small process here, it will be quite energy intensive. So we're trying to see here and compare the different processes. So if I revisit all the processes before, mechanical, microwave pyrolysis, and then the conventional heating is very energy intensive. So we're interested in microwaves here because not only is it energy intensive, but there should be a benefit, because if you're not putting a lot of energy into the fibers, you're not damaging them. So if you can design a process which is energy intensive, it means what you recover is actually high value. So there is a collateral damage associated with energy input into materials. So we are looking at that and how you can, so if we can optimize this and bring it down, we should be able to get better fibers. So so we're looking at the processes here. I assume that the chemical process will be somewhere here, far much even better, because we don't have as much energy as compared to other processes. But it might have other environmental burdens associated with the use of chemicals. So the vision here is that we want a recycling process which is high recycling rate, but also low energy intensity. So that's where we want to operate. And we are looking at that by comparing the energy intensity and the recycling rate. So to summarize, why is this important? It's important because if we look at virgin materials, raw materials, they are very energy intensive. So this is carbon fiber composites, about 180 something, and this is glass fiber, and then compared to other steel. So they're very energy intensive to make. So the environmental burden is quite high in producing raw materials. But let's look at that in context to actual fabrication processes. So the environmental burden of raw materials, of manufacturing processes, of recycling is very, very low. So the recycling energy is significantly low compared to the energy that we need for virgin materials. And some recycling processes can generate residue, which can be energy rich, which could be a source of energy for other processes. So our goal is to utilize end-of-line and composite waste as an input to manufacturing processes. And for example, the model that we've done, we are looking at 0.27 megajoules per kg for processing CFRP using the mechanical process. The main observation I'm making is that the faster a process is, the more energy intensive it is. And microwave pyrolysis is promising in terms of energy efficiency, and in terms of the quality of fibers we can generate, because we will reduce the collateral damage. And we are developing more energy analysis for other processes. I want to stress that energy usage is the biggest environmental burden in terms of materials processing, because from energy we can link that to CO2 footprint because it's a simple conversion factor depending on the carbon intensity of the electricity we are using. So if we can reduce the energy intensity of the process, then we improve the carbon footprint. And I want to stress that not all recycling processes are created equal in terms of energy efficiency. We should be working on recycling processes that are more energy efficient if we are to claim that it's better for the environment. So recycling helps us to extract more from less to cascade value. So we are reusing materials with energy already invested. We think that there's even a greater incentive to look at energy intensity because we reduce the collateral damage if we do not put significant energy into the materials during processing. So there are a number of companies already doing recycling of composite materials. So this is not just an academic topic, but there are a number of commercial applications here. So before I conclude, so the work we have just presented is part of our Exhume project and our creative outreach for resource efficiency project, where we're trying to find more and sustainable ways of recycling materials and to create data sets for life cycle assessment so that we can assess the environmental impact of recycling. Thank you.
Thank you very much. We have the time for questions. Yeah, please.
Here, the composite used is mainly carbon fiber and the glass. Yes. I'm wondering if it is possible to separate this composite firstly, I don't know, separate the constituents firstly in a chemical way. It's energy consuming very much this way. Is it possible?
Yes, so you can do that in a chemical way. That's done in a chemical way, yeah? I admit that the chemical way is the least energy intensive, but there's also an environmental burden associated with the use of chemicals. I focused on energy, global warming potential, but there are ecotoxicity and other environmental burdens that I have not assessed. So the chemical way is good in terms of energy, but it introduces other environmental burdens which you will not find in a mechanical or maybe microwave. Yeah. But we are also developing chemical process, and we find that to be quite effective. So we're looking at a range of processes.
Other question? Yeah.
Really interesting talk, but I would say that you see individual process, the mechanical, chemical, they are separate, or you combine both in order to get best from it?
Thank you. I have presented individual processes, and you're absolutely right. Hybrid processes or assisted processes might actually generate better results. Microwave is something else. The lady asked about chemicals. So the assisted processes, there is not much work at the moment done on assisted processes because we are still optimizing the individual processes. But I think in the future, we'll be looking at assisted processes so that we can take advantage of the benefits of the separate processes. So yeah, that's an important way to go for the future. Yes.
Other question? I have two. My first question, yeah, because you make a nice introduction to my talk. I'm going to speak about the recycling of CFRP using supercritical fluids. Yeah, why did you consider in your study just the UK market as for the sources and not a more global market?
That's good. And the second question?
Yeah, if you want. You are developing your technology regarding the energy demand of the process. What is about the reuse of the carbon fiber? Because depending on the process, you will have different kind of fibers, different kind of lengths of properties?
Okay, yeah. Thank you. The first question is, why are we considering the UK market? It's quite simple. The UK government pays for it. So the UK government pays for the research. So because of that, we're not allowed to consider other markets. But if we find collaborators in Europe and we work on a European projects, then we can consider other markets. I think it would be good to get a global contribution and compare the results. I think that's why these conferences are important. And the second question was?
You present the development of technology regarding energy consumption. What is about the reuse of fibers?
Yeah. Again, an important question, because as I have shown, there's a quite wide range of quality that you get from the recycled fibers, and we think that the quality should be matched to the application, and that's quite important. And we have a number of applications that we're developing, which I haven't reported here because some of them are still under protection until we decide which is the best way to exploit it. But I think the best way, the way forward is to tune the recycling process to the downstream application, which is going to take the waste. So that's absolutely important, yeah.
Thank you very much. Let's thank our speaker again.